Okay, I think we can get started. It's 6 o'clock. Welcome back, everyone, to the Advanced Machine Learning lecture series. Last time we started a very important section of this lecture series, which deals with randomness and probability. Because if you want to apply advanced methods of machine learning to anything in the sciences, then randomness is important to treat. And so you have to know probability theory and information theory, statistics. And we started by explaining Shannon's information theory, or at least a small part of it, that led us to the definition of entropy. And the way we did it was by talking about compression. How can we efficiently compress data? And so that's where I want to start today's lecture. Okay, so we asked if we have a source that emits a sequence of symbols, for example, a text made out of words, then how can we efficiently compress these symbols? And we understood relatively quickly that it depends on the probability or the frequency with which these symbols occur. And the very simple rule that Shannon realized is that the more frequent a symbol is, the shorter should be the encoding. And so I've tried to represent this here. If you were to encode some words, let's say you have a little dictionary of words that can occur in your texts. Some of the words are more frequent, and of course you want that the more frequent words are encoded in a shorter code. And that can be seen here in the word apple, which is relatively frequent. We say that it should have, say, only a code that uses up 2 bits. And the way you would read off such a code in the tree that I've drawn here would be very simple. You start at the root of the tree, that's the top, and then you go down the tree and you always pick the branch that you need to pick in order to go to the word you want to reach. And in this case, you first take a right turn, that is the 1, then you take a left turn, that is the 0. And so you already end up at apple, which is then encoded by 1, 0. So it only uses up 2 bits. But of course, things get more interesting if you want to reach another word that is far less frequent. Then you can afford to use more bits for the code, like ingenuity. And there you need to go through left, right, left, left. So that would add up to the code 0, 1, 0, 0. And so you see the whole game is to construct such a tree that gives you the encoding in such a way that the frequent words are reached very quickly and the not so frequent words are not reached very quickly. Now, we also discussed a little bit more in detail how the length of these optimal codes is related to the frequency or to the probability to find such a symbol, such a word. And what Shannon tells us that if you have a probability PS of finding a symbol S, in this example, the symbols are words, then you should take the logarithm to base 2 minus that. And maybe you have to round up. And that would be the length of the code in bits for this particular symbol. And what he then showed is, so this was for a particular code, the Shannon code. What he then showed was that even if you take any arbitrary code and you take the average over all the code lengths weighted by the probabilities, so something like sum over PS, LS, then this is always greater or equal than some lower bound. And this lower bound can be written down very easily, again, in terms of these probabilities, and it is what is known as the entropy. So that's where the entropy comes in information theory. Okay, so that's the entropy for us. And what I'm trying to do now in the next 10 minutes or so is to discuss with you some of the most basic properties of the entropy. Of course, those of you who have studied physics already recognize this as basically equivalent to the entropy you know from thermodynamics or statistical physics, except that there possibly you would have a natural logarithm, and also you have a Boltzmann constant in front, but these are minor details. And so when Shannon discovered this formula, he asked John von Neumann, the famous mathematician, okay, how should I call it? It looks kind of like the entropy in thermodynamics. And apparently John von Neumann told him, well, just call it entropy. No one really knows what entropy means, so you always will have an advantage in any discussion. Well, okay, so now let's have a look at a few properties of the entropy. So the first thing is I want to write down the definition again, but maybe in a slightly more general format. I want to say if I have a random variable, let's call it x, which can take a number of discrete values, like the various symbols that we discussed, or the integers, or something like that. Then the entropy is defined in the way we wrote it down. I just write it down again. Probability of the random variable, assuming the value little xj, this is one of the discrete values, times the logarithm p of x equals xj. And to make it really clear, we put a base to the logarithm. So the logarithm is base b, and what Shannon was using is, of course, base 2, or we could also be using base e, and so on. The numerical value of the entropy, of course, will be slightly different, but it's only a multiplicative prefactor, so it's not so dramatic. Good. We can apply this to the case of a random variable that only can take two values. This is the simplest case. And then we can make a plot of the entropy in that case. So if our random variable can only take two values, let's say 0 and 1, then if I plot the probabilities, I might have such a situation that one of those values is much more frequent than the other. Let me call that p. And then by normalization, of course, the other one will be 1 minus p. And so the h, the entropy for this case, will be minus p log p minus 1 minus p log 1 minus p. And here you see that I already don't write the base anymore at the logarithm, but if I want to tell you the actual numerical values, I will have. And so we can plot this function as a function of the probability p and see which values it takes. And so the first thing you notice is that the function is symmetric when I let p go to 1 minus p. So it's somehow symmetric around p equals 1/2. The second thing you notice is that if I send p to 0, then both terms will actually go to 0. It's obvious for the second term because 1 minus p is then 1 and the logarithm of that is simply 0. It's not so obvious maybe for the first term, p log p. When p goes to 0, the logarithm explodes, the p goes to 0, so which one wins? Well, in fact, the logarithm is so slow that it still goes to 0. So we have 0 both at p equals 0 and 1. And then finally, you can work it out for p equals 1/2. The logarithm to base 2 of 1/2, of course, is minus 1, and overall you get 1. And then you can interpolate and you get a curve like this, which is nicely symmetric. And I should also note that the slope at 0 in principle is infinite, but you wouldn't easily see it if you do a numerical plot simply because the logarithm is so slow and going to infinity. Okay, so that's the first example. So what are the general properties of the entropy? The first thing is, in this example, we already saw it was never negative, and that is a general property. And this simply follows from the probabilities being less than or equal to 1. Okay, the second thing is if you calculate such a discrete entropy of a discrete random variable, it's even bounded from above. And the largest value that you can take is the logarithm of n, if n is the number of different values that your random variable can take. And so this would be achieved in the situation where you have an even distribution over all the n values. Okay, fine. So these were relatively simple. The next thing is very important. The next thing is additivity. So imagine you have two random variables, but they are independent. Now, if they are independent, what we mean by that is that the probability factorizes. So the probability of observing capital X to be some value little x and capital Y being some value little y is just the product. Maybe to be careful, I want to put a subscript here. Okay. And so then it turns out that, well, first of all, the entropy is defined in a manner similar to before. So I would have to sum over all possible values that this joint random variable can take, where I have to specify both x and y. So I really have to sum over all possible values of little x and all possible values of little y. So that's the definition. And then you can see what this gives you in this particular case when the probability factorizes. And the most important thing happens under the logarithm, obviously, because the logarithm of a product is, of course, as we know, the sum of the logarithms. And so once you insert that and work it out in a few lines, you find immediately that what you get is the sum of the entropies. So for two independent random variables, you can just sum the entropies, and then you get the entropy of the joint distribution of both random variables. So that's very convenient. Of course, it's also a property that you may know from the thermodynamic, the statistical physics entropy. It is sometimes called extensivity. So it means things such as if I double the volume of my large system, then the entropy also doubles. By the way, one can also turn this around. Maybe you know this. If I'm looking for a functional of the probability distribution in such a way that it is additive, in the end, I automatically have to arrive at the entropy in this form here with a p log p. Okay, so what happens if when my two random variables are not independent? Then, of course, this doesn't hold anymore. But in general, still something holds. Namely, in general, I have an inequality. So the entropy of the joint distribution might be less than the sum of the entropies. And so to understand this thing, I can plot for you a situation where, let's say, along one axis we plot x, along the other axis we plot y. Of course, we only have a few discrete values. And then I can try to plot the probability distribution. Maybe I put a big circle when the probability is large, and then maybe I put smaller circles. So I could have such a situation, and you clearly see that x and y are dependent on each other. If I tell you the value of x, you immediately know the value of y. And what happens now is if I only look at the distribution of x, I could plot this on this axis. It's rather wide. It has many different possible values with a finite probability, so it has a large entropy. If I plot the distribution of y, maybe on that axis, I observe the same kind of effect. But since they are dependent, they only fill the joint distribution only fills the possible slots on the diagonal when x and y are equal. And so its entropy is actually less in this case than the sum of these two entropies. So by looking at the joint distribution, you recognize that there is more structure and less randomness than you would have expected if you only were to look at the so-called marginal distributions of x and y. So these distributions when you forget about the other variable. Okay, so the important property, additivity, or at least if they are not independent, then you have this inequality. And then I want to add one final property to this list of properties, and that is also quite interesting. So imagine you have the following situation. Again, I want to draw a probability distribution. So here, 3 possible values. And here there will be another probability distribution. Again, 3 possible values. Let me say I have something like this. So one of the probabilities is 1, all the others vanish. And we know already, or we could calculate quickly, the entropy is 0. And then I have another probability distribution where the same happens, but at another spot. So let me call this, I don't know, P, and let me call this probability distribution Q. And let me then say I have a new random variable which is distributed according to some mixture of these two. So what I mean is I have a new probability distribution, let me call it P prime, which is lambda times P plus 1 minus lambda times Q. And of course, the way this looks like, I can plot here. I just have a weighted superposition. So depending on the value of lambda, maybe there is only a little contribution from the P distribution and a lot of this contribution from the Q distribution. In any case, I have a mixture. And what you immediately see is, of course, the entropy of this will have become larger. So what is true in general is that the entropy of that distribution is larger, or at least equal, than the entropy, than the corresponding weighted sum of the individual entropies. So maybe I'm abusing notation a little bit. Previously, I had as argument the random variable. Now, for a moment, I'm putting there the probability distribution belonging to the random variable, but you know what I mean. And so this property is known as concavity. It's basically if I have two probability distributions and I'm somehow mixing them, which I could, then the entropy will not decrease, but probably increase. So mixing two distributions I could simply do by saying I throw a dice, and depending on the outcome, I will then afterwards sample from one or the other distribution. So that's how you get such a mixture of distributions. Okay, so I hope these properties are clear and probably you have seen them somewhere already. If not, I think this is all intuitive. What we now want to do quickly is discuss a little bit the case of continuous random variables. So that's something slightly different. And we need to discuss it a little. So think of the position of a particle in physics. the particle is fluctuating around, then it has a continuous position that is fluctuating. And so what we would introduce for continuous random variables in general is, of course, a probability density. So I plot the probability density versus x. And you know, the meaning of this probability density is, of course, if I ask what's the probability to find my random variable within a small interval, let's say of size delta x, then the probability is obtained by taking the probability density and multiplying by delta x. So probability of finding my random variable within a small interval is delta x times p of x. So if delta x is large, this is only approximate, but if delta x goes to 0, this becomes perfect. So that's a probability density. And the question is now, what do we do when we want to discuss entropies for such probability densities? And if we don't have a better idea, maybe we should discretize again. And there's even a good reason for that. Namely, if you want, in the sense of Shannon, to finally encode things in a binary code, you have only a finite resolution. You can only assign a finite resolution. And so you have to discretize anyway. So we will discretize with some resolution, let's say epsilon. And so I would then have the same picture, of course. But I have introduced new bins. And I count everything that sits inside one of the bins. Okay. And so now I have a new discrete random variable. This was size epsilon. And I can say my probability to get the value j of this new discrete variable depends on what's the probability density around j. So if epsilon is small enough, it's just epsilon times the density at xj. Okay. So now I'm back to the old case, and I can immediately apply my entropy. So I can say the H calculated in the usual discrete way of this new discrete random variable that can only take these discrete values is just, well, we have seen it before, minus some j, p, j, log, I won't specify the base anymore, log pj. And now I can insert the definition I have up here. So it's epsilon times the probability density. And that's quite interesting, because if I now write it explicitly, I will see two interesting things. So the first thing is, if I like, I can, I can say my epsilon is a little bit like a dx. So as if I'm doing a integral by a Riemann sum. So I could say this is something like minus integral dx p of x log epsilon p of x. Yeah. So if epsilon is small enough, this will be good. But then you see this can be subdivided into two parts, because the log of epsilon times p of x, of course, according to the usual additivity, is log of epsilon plus log of p of x. And so the log epsilon part, of course, does no longer depend on x. So I can carry out the integral, which is easy because the integral over the whole probability density, p of x, is just 1 by normalization. So what I get in the end is minus log epsilon minus integral p of x log p of x. And so now that is an important formula, because it suggests to us how to define an entropy measure that is only dependent on the probability density. So the suggestion would be, let's take this part and let's define it as an entropy for continuous random variables. But we should never forget that there was also this first part. Yes, and thank you for the question. Isn't there an issue with convergence when we take epsilon to 0? So I will not ever set epsilon exactly to 0, at least not when looking at this formula. But I will point out that, of course, as you also anticipate, if epsilon goes to 0, the log of epsilon goes to minus infinity. So this first term becomes plus infinity. And this will come back and will be important in a moment. But for now, let me just use this formula for a sufficiently small but still non-zero epsilon. And let me use this formula as inspiration to say I keep the second part and I define it as what people call the differential entropy. I can do that. I just need to keep in mind that there was this funny other term. So sometimes to make the distinction really clear, people even use a small h. I will not consistently do this, but for now, maybe let's do that. I just say that's minus integral p of x log p of x dx. I can certainly do that. Now, if we do that, we see that it has some properties that are still nice and good and comparable to what we discussed before for the discrete case. But there are other properties that are a little bit funny, and they are a little bit funny exactly because of this log epsilon term that we, so to speak, discarded. And so the first thing is h is no longer necessarily non-negative. In fact, it can be quite dramatic. So consider the following probability density, namely a delta distribution. So that at least can be constructed as the limit of distributions that become more and more narrow. It's basically a deterministic variable again. And if you look at it, I need to be careful. The h, the differential entropy in this case, is minus infinity. So not only does it no longer be non-negative, but it even can get minus infinity. So the old case where we had 0 for a perfectly deterministic variable in the discrete case now turns into a case where we get minus infinity. And if you look back at the old formula, this is perfectly reasonable. So whenever you discretize, on the left-hand side, you will have 0, because regardless of how small you make epsilon, there will only be one bin with a probability of 1. So h is always 0. But on the right-hand side, we have two terms. We have the minus log epsilon term that goes to plus infinity if epsilon becomes very small. And we have this minus integral term, which is the differential entropy, which, as we just saw, goes to minus infinity. So everything is consistent. It's just something we need to keep in mind. Okay, so that was the first thing. Also, there is no upper bound. The reason for that is, of course, I can just spread the continuous random variable more and more, at least if I'm working on the real line. So there's also no upper bound. But other properties still exist. So for example, additivity. So if X and Y are independent, I have what we had before. So the joint entropy is the sum. Okay. There is another slightly funny thing going on with the differential entropy. And in order to appreciate this, let me go back for a quick moment to the entropy for the discrete case itself. So I could have a probability distribution like this. Okay. And now I could turn it into another one simply by permuting entries. So these were labeled 1, 2, 3, 4. Maybe I can label them 1 prime, 2 prime, 3 prime, 4 prime. But now let's say whatever had been 4 previously, I have now labeled 3 prime. So the probability appears here. Whatever had been 2 previously, I now label 1 prime. And so on. Yeah, so. Okay. So if I'm permuting labels, what does that do to the entropy? And the funny thing is the entropy doesn't change. The entropy doesn't care about how you label your discrete events. So that's somehow nice. The entropy does not depend well, on how you label the events. That's in particular important if your events do not even have a natural ordering. So you are not talking about integer numbers, but about words. Let's say there may be not any natural ordering. So that's nice. That brings up the question, what is the closest analogy to a permutation in the continuous case? Well, I would say it's something like a bijective mapping. So let's consider bijective mapping, which just means I take my old values X, I apply a bijective one-to-one function to it, and I get new values Y. So something like here's X, here's Y, and then I just, in 1D, I would just need a monotonously rising function, something like this, that would do the job. So that's bijective. The question is, what happens to the differential entropy if I implement such a bijective mapping? The most optimistic scenario would be that it does not change. Unfortunately, that's not true. And so we have to check what is true. So for that reason, we want to see if I know the probability density for X, then what is the probability density for Y? Well, you have probably seen this before, but we would say things like this. If I multiply the Y density by some small interval dy, I get some probability, just like before. And this should be the same probability that I would get if I multiply the X probability density at the corresponding value of X that corresponds to this value of Y, because there's bijective mapping, and multiply with the corresponding interval of X. So it's basically like saying, I can look at this X interval, or I can look at the corresponding Y interval. But they represent the same thing. So if I calculate the total probability in each of these intervals, it's the same thing. Okay. We need to be a bit careful because It could be that this is a monotonously falling function, so then dy has a different sign than dx. So to be really on the safe side, maybe we want to put a magnitude sign here. Now, dy is, of course, dy over dx times dx, which is, we could say, f prime times dx, so the derivative of f times dx. Okay, and so if I now collect everything, I could say the probability density for my variable y is just the probability density for my old variable divided by f prime of x. And in order to make everything a function of y, I want to express the x sitting inside that argument as a function of y as well. And in order not to get into trouble with the sign, I take the magnitude. So this is what is happening. You can also convince yourself from a graphical construction like the one shown above that this is really what you need. And maybe you have already seen this thing. Okay. And so now I have the old probability density for x. I have the new probability density for y, and I can insert this into my definition of the differential entropy. And so what I find is then they are, well, almost equal, except there is an extra term that comes from the division that I introduced here. And so this extra term is integral log f prime of x p of x dx. Yeah. So we get an extra term. We cannot avoid that. And this extra term is not a mere constant in the sense it does depend on the probability density p of x. So where it is concentrated and what is the derivative of f doing at those points. So we cannot avoid that. If we start let's say stretching or changing our coordinate system, in essence, we're changing our coordinate system, then we pay the price of having a different differential entropy. You may also ask how this works out for higher dimensions. Here we only did it for one dimension, and I just quickly give the formula. It's essentially a Jacobian determinant that enters here from the coordinate transformation. So instead of f prime, I need the determinant of the Jacobian matrix. And we already know what is the Jacobian matrix, of course. That's the matrix that contains all the derivatives of this function f. Okay, so this is something you have to live with for probability densities. Good. So this is all I wanted to say at the moment about entropy. We are about to start the next chapter. But are there any questions here? Okay, I don't see any questions. Now, this is entropy, but that's only the starting point of our journey into probability theory. And the next chapter is particularly important. It's about Bayes' theory. And I want to start with a motivation. So what is this about? It's one of the most important concepts, especially if you think about scientific discovery. So you make an observation, which is, of course, a central part of doing science. And then you can ask yourself multiple questions. I've tried to list some of them here. The first question you could ask yourself is, what is the most plausible explanation for this particular observation? Maybe it can be explained in several ways, but what do I consider most plausible? Also, once you make the observation, you have learned something. So you could say, how should I update my knowledge about the world given this observation? Is there a systematic way to update my knowledge? And then even more specifically, you could say, well, how much have I learned about the world from this observation? And you could say, well, in a sense, previously I was very unclear about what state the world is in. I didn't know many things. Now I know a little bit more, so I have reduced my uncertainty. And if you look carefully at these sentences, there are some keywords like plausible or uncertainty, and all of them have to do with probabilities. So what you're really asking about is, what should I do with probabilities when I'm making an observation? And I want to, before going into the mathematical details, I want to give an example of a situation where this is clarified. So on the left-hand side, I show a kind of picture. Let's assume it's a photograph. That's the observation. So you see a tree and a house. And then on the right-hand side, I write down a possible explanation for what is the real state of the world that could have produced this picture. And the explanation in this case is obvious, right? We have a house and a tree. They are of typical size and they are standing right next to each other, and we took a picture, and that's how it looks like. In fact, this sounds so reasonable that we don't even try to come up with an alternative explanation. So that's fine. But then let me switch to a different photo. Let's say this is the observation. So you see a person standing next to the house, but something is a little bit odd. If you compare them, it seems like the person is, I don't know, 3 or 4 meters tall. So can we still use the old explanation where we say, well, there is a house and a human, both of typical size, they are right next to each other? And we would say no, because if that were the case, if they are of typical size and next to each other, then it should never look like that. Then the human should look smaller or the house should look larger. So it's impossible. This observation cannot be explained in this way. And so we have to start looking for different explanations. We could say, well, maybe we have a giant here. But then we know that giants are not so frequent in the real world. So maybe we want to put this possible explanation in brackets. We could say, well, maybe this is a toy house. So the house is actually smaller than you might think it is. That could make sense. Or maybe this is just a matter of perspective. Maybe the human is much closer to us and it just looks like the human is standing next to the house. And so these are all possible explanations that previously for the other case, we didn't even consider because they are relatively rare. Yeah, you don't often see pictures of toy houses outside. It's much more frequent to have pictures of real houses. Also, you don't often see pictures where the perspective is really strange, so as to make things look differently sized than they usually are. So usually we would say these are very unlikely possibilities, but since we ruled out the first one, this is probably what we are stuck with. And so this is already a first example of Bayes type reasoning. And if you look very closely, there were 2 ingredients. There were a range of possible explanations, and we have an idea of how probable these explanations are in the world. When I look at pictures, how often is this picture a picture of a toy house? How often is it a picture of a real house with a real human standing next to it? So that was one part, the intrinsic probability of these possible explanations. But then there was a second step where we say, well, given this explanation, is it compatible with the observation that we are seeing? So there were these 2 pieces. And so let's then switch to discussing this in mathematical detail, and we are going towards the Bayes formula. But before we go there, we have to talk briefly about conditional probabilities. So we define a conditional probability by saying some event A given some other event B, what's the probability for that? The conditional probability. Well, that's the probability for observing both events at the same time, divided by the probability of observing event B. Okay. And so now we can turn this around. Let's say I want P of B given A. Now I can apply the same expression, so that would be still the probability of both together, but now divided by A. And I can then express P of A comma B by the first line formula and write it like P of A given B times P of B, and then divide everything by P of A. And so there it is. This is Bayes' formula. Okay. Now, just a quick side note, of course, the P of A in the denominator, if you want to write it more explicitly, you would say, I can take the same expression I have in the numerator, but instead of only taking it for a particular event B, I sum over all possible values of B. And so you see this is a kind of normalization. Here I'm assuming, by the way, that all the B prime are separate elementary events, so that I'm not summing anything twice. Otherwise, you have to be more careful. Okay, so what does that give us? What it gives us is we are basically inverting the order. I want to know what is probability of B given A, and I express it in terms of probability of A given B times P of B. And so that's very important because I can immediately apply it to our setting from before, where we had an observation and a possible explanation. So we could say, what's the probability that a possible explanation or model of the world is true given the observation? And I can use a Bayes formula to revert the order. I can say, well, what's the probability of making this observation given that I assume the model is true, times the intrinsic probability that such a model is true, or that this explanation is true. And I have to divide by the overall probability of this particular observation given any model. So I sum, so to speak, over all possible models, just like we said above, I normalize. Okay, so you see how that can become an update of our knowledge. Previously, we had some understanding, and we need to discuss this, but we had some understanding of the probabilities for various models of the world. And then afterwards, we update this given the observation. And so what this means is that we will shift around probability, and some of the models will now be seen as being more probable given this observation, and some models may even be ruled out, so their probability may be set to 0, namely in those cases where the observation is completely incompatible with the model. So this first piece would be exactly 0. And so I claimed in our example, the first explanation is exactly of this kind, because if they are of typical size and next to each other, then I would never see this particular picture. Okay, good. And so now we want to get a little bit more mathematical. I don't want to always write model and observation, but also not simply A and B. And the way I like to express it in the following is that I imagine just for a moment that all my models are parameterized. So I would say lambda is the parameter of my model. And you can imagine even a vector lambda, so it can contain a lot of information, or it could be a discrete lambda that enumerates all the different models. It can contain a lot of information. And the observation I will often call y. And again, it could be a vector, it could be something complicated, so there's not really any constraint here. And then the p of lambda, or the probability of a certain model that occurs in the formula before, we would call that the prior distribution. It is prior before our observation. And then P of lambda given y, so to speak, probability of a model given the observation, we call that the posterior distribution after the observation. And then finally, we had another crucial term here, which was the probability of the observation given the model. So in our new language, that would be P of y given lambda, and that we would call the likelihood. So that's the likelihood of making a certain observation given a particular model, assuming a particular model. As you can already guess right now, the most problematic aspect of the whole thing is the prior distribution. And you have to make up your mind about it, and we will say more about that later. But the rest follows almost mechanically. So the likelihood, you should be able to calculate the likelihood. If you understand your model and what it means in terms of the observations, then you should have a model of the statistics of observations given the model is true. And then the posterior distribution just follows from Bayes. So the prior is the most problematic aspect, but we will discuss it. This here imagines there's only a single observation. But of course, we can also apply exactly the same reasoning to a sequence of observations. And the one way to do this is to say, well, I have exactly the same formula essentially, but instead of having a single value y, I have multiple values y representing the sequence of observations, but I can still reuse the old formulas. It's just a higher dimensional observation, so to speak. And then I can use Bayes, so I invert the order. What's the probability of observing all these things together, given the model lambda, times P of lambda, and then divided by the normalization. Okay. Now we can still simplify it, because we can say, well, to observe this whole sequence of observations given lambda, I claim each of these if each of these observations is independent, which very often is the case, then I can just say, well, that's the product of the individual probabilities to measure the individual y given lambda. Okay. So this is true unless we, for example, have a situation like in quantum mechanics where one observation will perturb the system and then funny things can happen. But in general, if I imagine a classical system where the measurements, where the observations do not perturb the system, I just have a given model and I do all these observations. They may contain some noise, some measurement noise, but they are independent. And so I can write it like this. Okay. And so what the sequence of observations will help me with is, of course, to become more and more certain. Because just as an example, if the probability of an observation under a given model is already relatively small, and then I keep observing, what these terms will do is they multiply many small numbers, and then the overall probability for making the sequence of observations is even smaller, exponentially small, in which case I can then rather confidently rule out this particular model. So that's the purpose of making repeated independent observations. Okay, so quick side note. You see that here I have a product. And so this product then also enters the right-hand side of the base formula. And there's a nice way to express this product in a different way. Remember the entropy. If we apply the logarithm to a product, of course, we get the sum. And you can do the same here. So you would say log of p of lambda given y. So that would be the log of the left-hand side of Bayes equals, and on the right-hand side, I already use the fact that I have this product, and I will say sum over j log p of yj given lambda. Then there's still the log of p of lambda, that was the prior distribution. And then there is, of course, the log of the normalization part. The normalization part, this last part, is independent of lambda. So it's not particularly important. It's just there, as we said, for normalization. But these other parts are important. And this part even has a name. It's called the log likelihood, because p of y given lambda is the likelihood. The log of that is the log likelihood. And so that often plays a role in many machine learning applications. Watch out for the log likelihood. Okay. Oh, I should still add, this is true for independent observations. Here's a quick side note, an interesting remark. Given lambda, these observations are independent. But once I calculate, for example, p of y in the denominator, where I average over all possible lambda, I will in general observe that p of y is not a factorized distribution, because via lambda, they do become dependent on each other. So think about it a little bit. One always has to be careful. But if the model lambda is fixed, then this is a good assumption. Okay. And so is there any question at the moment? We will go through many examples and apply this to many different cases. So all of that will come, but is there a question here? Doesn't seem to be the case. Then let me jump right away to physics examples, because it's so nice to explain Bayes in terms of physics. So the first example I want to give is qubit measurement. But don't worry, even if you have no idea about quantum mechanics, you can still perfectly understand it. So of course, a qubit is a quantum mechanical two-level system, but the fact that it is quantum mechanical, we will not really need here. So think of it as a thing that can be in one of two states. And now I want to measure it. And there are many physical situations where I can have a continuous measurement signal. whose values depend on the underlying state of the qubit. And so what we are talking about now are actually two different probability distributions. So one of them holds in case the qubit is in one of its two states, and the other holds if the qubit is in the other state. So again, this would be the probability of, or the probability density in this case, of observing the measurement signal y given, say, lambda equals 1. So the model now is just the state of the qubit, which we do not know, but we want to learn something about it. And the red one is the probability density given that the qubit is in state 0. Okay. So now, even without writing down Bayes' formula, you can already guess what happens. If you measure y somewhere here to the left, you will be very confident that the qubit is in state 0, because if it were in state 1, it's very unlikely to see any measurement value down there. If you measure here, you're pretty sure it's in state 1. But if you measure somewhere in between where you have overlap, it's not so clear. Yeah. And so if I now do apply Bayes, I would say the updated probability of saying my qubit is in state 1, given I have already measured, is, well, I turn it around, y given lambda equals 1 times prior probability of lambda being 1 divided by the normalization. And now let me just write down the normalization explicitly. There I would basically take the same numerator and just sum over all possible values that lambda might have, which in our case is, of course, only the two different states. Okay. So that's Bayes' formula. And how does this look like? Well, if I do only a single measurement, so that's y versus the measurement step. So let's say this is the first measurement. And I get a value that is, let's say, positive. Then I might think, maybe lambda equals 1. Maybe my qubit is in the state 1 because it's positive, so it's more somewhere here. But it could be a fluke. It could be just by accident, by random chance. And then maybe in the next measurement, I see something negative. And then in the next measurement, I again see something negative. And eventually, I see that my values tend to be more on the negative side. In this case, probably after some time, I will conclude that my qubit is actually in state 0. So what you could be plotting as well is, say, how the probability of being in state 1, given all the previous measurement results, evolves during time. So J is always my time step. And we said maybe initially the prior probability was 1/2, 1/2. So lambda equals 1 and lambda equals 0 were equally likely. So we started out at 1/2, somewhere here. Then the first measurement even preferred, this is the first measurement, it preferred lambda equals 1. So Bayes would tell you that you go up in probability. But then the next measurement, it discouraged this interpretation that the qubit state is lambda equals 1. So you go down again. And then you go down again. And so this would fluctuate up and down, but eventually it will converge to 0. So this is a typical Bayes update trajectory for the measurement of the state of a qubit. So you learn more and more as time goes on. Okay, so that's the first physics example. You see how the probability that is updated fluctuates, but eventually it catches on and you get some definite outcome. Let me move to the second physics example, which even demonstrates another interesting point I want to make. So the second physics example is also nominally from quantum physics, but again, you don't really need to know quantum physics. So it's the decay of a cavity. What is a cavity? A cavity is just two mirrors. And between these two mirrors, I can have photons. Maybe there is a few photons, that is packets of light energy bouncing around between these two mirrors. And once in a while, the mirrors are not perfect. Once in a while, one of the photons escapes. Because it passes through the mirror. And when it escapes, I can be smart and I can place a detector outside. So this is the typical sign for a detector. And if the photon hits the detector, then the detector will go click. So this is, so to speak, a measurement of photons leaking out of a cavity in a nutshell. You don't really need to know much more for our example. So there's a handful of photons, but the interesting piece will now be, I don't know how many photons there are. There's a probability distribution. And by observing some of the photons leaving the detector, I want to update my knowledge. I want to update my probability distribution. Now, one of the first things that Bayes needs is the likelihood. So given the model, what's the likelihood of a certain observation? So my model here is just specified by the number n of photons inside the cavity. Okay. And then what's my observation? Well, that's just whether there is a click in a short time interval or not. So the probability of having a click in a short time interval, that's my likelihood. That's what I look at. And now, in order to work this out, you would need to know a little bit of quantum optics, but the result is very reasonable. So first of all, the probability increases when the time interval tau is larger. It also increases when the decay rate is larger. But this is just a numerical prefactor. And the probability increases when the number of photons is larger. It also makes a lot of sense. If there are more photons inside the cavity, the likelihood that in a given short time interval, one will exit the cavity is also larger. So this is the likelihood that we will need for Bayes. So observation given model. Now, immediately I can apply Bayes and I can say, well, tell me, what's the probability that there are n photons inside the cavity, given that I have observed a click? Well, I just invert. I reverse the order. I mean, click given n times p of n, which is the prior distribution of the photon number, divided by the probability of getting a click at all. Okay. And so now we don't need to calculate the details of this. Maybe you can do that in a homework, but I want to show you an example of what can happen. And it's quite counterintuitive in a way. So let me say I have a certain prior distribution. So the photon number is, of course, some integer. And let me plot this. Maybe it's mostly 0 photons. So this is a cavity which to a high probability is empty. But there is also a small probability to have 1, 2, or 3 photons. Okay. So this is the prior distribution. Now assume I do observe a click. Well, immediately I have to apply Bayes and I have to update my knowledge. And to be very precise in my language, n is still the number of photons that were there in the cavity initially. It's clear that there is another physical process on top of that, meaning that if a photon leaves the cavity, you have to reduce the photon number by 1. We will discuss it in a moment. But n is always the random variable that tells me what is the number of photons at time 0 before everything starts to happen. Okay. And now I have a click. But since I have a click, I have to multiply P of n, the prior, by the likelihood. And you immediately see that for n equals 0, the likelihood here is also 0 because it's multiplied by n. So immediately I will set this one probability that was the biggest one previously, I will set it to 0. That's a drastic change. All the others are multiplied by n, so the larger the n, the more strong the enhancement, in addition to the enhancement that comes about because I have to renormalize, and now since the peak at 0 is gone, everything already wins. So in the end, I will have something like something like this. With a proper scaling, of course, normalization is still obeyed. So this is interesting. So that's the update that Bayes tells us. And what we immediately see is that the average photon number has increased. Yeah? Previously, it was close to 0 because that's where the highest probability was. And now the average photon number has increased, maybe something more close to 2. Okay. Now, of course, there's in addition the physical process that the final photon number after the event is, of course, if I did observe a click, is n, that is the number previously, minus 1. That's true, since simply physically one photon is leaving. But even though this is so, we can still, if the numbers work out, we can still have a very funny situation, namely that the final photon number, calculated according to the posterior distribution, is larger than the photon number calculated according to the prior distribution. So even taking into account that I'm taking out one photon in order to get the click, after the click, on average, I have more photons in the cavity than before the click. And when I first saw this many years ago, of course, it's a well-known phenomenon, I was really puzzled. But you understand it because you know Bayes. What happens here is, yes, there's the physical effect of subtracting one photon, but more importantly, the fact that you are detecting a photon outside means the probability distribution has to be updated. You learn something about the cavity, and so probably the cavity has a rather large number of photons inside, which previously you didn't know. Previously you thought that it's most likely that the photon number is 0. So it's your update of information. So something very counterintuitive, but immediately explained by Bayes. Okay. There's another interesting thing to remark here, namely the spread of n also increases after the click has been detected. Previously, the spread was very small because with high probability, n was 0. Afterwards, if you were to calculate, say, the variance of n, this has increased, and that can happen. And there's something else that happens here, which is that if you were to calculate the entropy, initially the entropy is very close to 0 because everything is dominated by this peak at photon number 0. But afterwards, it's more spread out, so the entropy is larger. So is there any question at the moment about the funny physics example? Yeah. Is the statement decay increases the expected photon number only true after the first click? Well, it depends very much on what was your distribution. So it could even be wrong after the first click, depending on what was the distribution. And eventually, of course, as you have more and more photons leaking out, eventually the photon number will decrease down to 0. Eventually you have none left. So it always depends on the distribution, and eventually it will go to 0. But intermediately it might jump up. Okay, good. So I just made a remark about how the entropy changes when you do this observation. And that brings us to an interesting little side topic, which combines what we learned about the entropy and what we learned about Bayes, and that is the conditional entropy. So let me just directly define the conditional entropy for you. It's conditional in the sense that I will calculate the entropy of some random variable x, given that I make an observation of another random variable y. Yeah, so like before, we had the observation of whether there was a click or no click, that would be y. And given that observation, I calculate the entropy of x, which in our example would have been the photon number. And so the way this is defined is quite interesting. So I'm taking the entropy calculated for the conditional probabilities. So wherever I had probabilities, I just put conditional probabilities. But then, and that's important, I still average over all possible observations. Let me indicate this like here. And so this average over all possible observations, of course, I have to put in my sum correctly. So of course, I sum over all possible x. At first, I keep y fixed, but then later in the average, I still also average over y, which is the possible observations. Now, if I want to write this explicitly, I would say this is minus the sum over x and y, the conditional probability. Let me shortcut it. So this P of y comes from the average over y times a log of the conditional probability. And so these two terms together here, of course, you recognize the conditional probability times the probability of what I am conditioning on. This is just the joint probability. So in total, this is the definition of the conditional entropy. Okay, so it's basically entropy calculated with conditional probabilities averaged over all possible values of the observation. And so that's a very useful quantity because you can show one thing: this conditional entropy of x given y, given the observation, is less than or equal than the entropy of x alone without observation. So that's an important theorem. And that I can say something about how this is proven in a moment, but that has an important meaning. So you would say, aha, on the left-hand side, I have a reduced entropy, apparently, if this is the inequality. And it's reduced because by measuring y, I have gained additional information about x. That was the whole point of making an observation, that you learn a little bit about the state of the world. And so just let me quickly sketch how this is done. H of x given y, you can also write as something else, and maybe I want to indicate it here. So you could always write this conditional probability as x comma y divided by p of y. And that's a nice way to write it, because the p of x comma y is exactly the same quantity as you have in front. So combining these terms, you would see, aha, this is just h of x comma y, the entropy of the joint distribution. But then there's, of course, the other term, p of y. And if you carefully work it out, you find that this other term is just minus h of y. Okay. And so now, why does this immediately then give rise to the inequality? So I claim this is less than or equal h of x. Well, you remember an inequality that we proved earlier today, which was just that the joint entropy of the joint distribution h of x comma y is less than or equal the sum of the entropies, and that's why this works. Okay, so that's nice. Okay, so immediately 2 questions. Haha, yeah, first question. In the previous example, h of n given the click was larger than h of n. Very good, you pay attention, yeah. So here I made a big point out of the fact that we got the click and the entropy increased instead of decreasing. And if you think about it, you see what happens. That was the entropy change if you had not averaged over all possible outcomes of the observation. But here I do average over all possible outcomes of the observation, and that's why this inequality is obeyed. So what happens in this case is there's still the no-click observation, which we did not treat here. And in the no-click observation, actually, you even enhance the peak at n equals 0, and so the entropy becomes even smaller. And the no-click event, of course, has higher probability. And if you then average over both the click and the no-click event and see the entropy changes in both cases, in one case it goes down and the other goes up, overall, on balance, on average, the entropy will decrease. So that's why the conditional entropy defined in the manner that I show here indeed decreases. Yeah, but it's an important example which shows that individual contributions can change with various signs. Only the average does what we expect it to do. Another question, is there a way to use Bayes' rule to derive a differential equation for updating a probability distribution based on observation of some continuous random variable? Yes, that's a very good question. And yes, indeed, this is true. So you could imagine very weak measurements where the likelihood function P of y given lambda is very spread out. So you don't learn very much by a single observation. And then if you apply Bayes, you see that the probability density in a single update almost doesn't change. It only has a slight tendency. And then you can imagine you do many such small steps, and eventually you take the limit of very tiny steps, but very many of them. And you can indeed, in principle, write down a differential equation, which of course will be stochastic because the outcomes of individual measurements are stochastic. And that takes you to the domain which in quantum optics goes by stochastic master equations and weak measurements. So that's a whole field in the theory of quantum measurements, which is very interesting and directly connected to Bayes. So you really take this limit of very weak measurements that happen very frequently. Okay, very good. So now we already discussed the very important fact that that we should repeat here, that the entropy goes down only on average. So only because we average over y. And so what this means in particular, that if I define conditional entropy conditioned on a particular value, which I might do of this form where I just take conditional probabilities and that's it. Then there is no guarantee. Okay, so that's the first important remark. But let's come back to the average case. So what we can do now is we consider the difference between h of x and h of x given y. H of x given y is the smaller thing, so this difference will be positive. And that thing has a name. It's called the information gain. Remember, we had derived the entropy in the sense of Shannon by looking at the information, which was the log of the probability. And here we would say that if the entropy decreases, we have learned something, so that must be the information gain. And to make it really clear, because sometimes these words are used imprecisely, I can even add an expected information gain. Expected means you average over all possible outcomes of the observation, you average over y. This is what we just said. This is important. Okay, very good. So that will play a big role when we later ask ourselves, how can I use Bayes to do optimal measurements? How can I ask myself, which measurement should I do if I have the choice between several in order to learn the most? And then the information gain obviously will be the most important quantity. But that's not for today. For today, we are happy if someone tells us this is the kind of measurement you do, that's the likelihood probabilities, and this is how Bayes works. Okay, good. So now we have also conditional entropy covered. And let me maybe end today with a bigger perspective. Right now in the examples, we were quite modest. We said, look, my model is the qubit state, or my model is the number of photons inside a cavity. And it is clear if I do a measurement, I learn something and I will produce a better probability distribution with less uncertainty on average, at least. But one can also take the bigger perspective in the spirit of artificial scientific discovery or the scientific process. One could say, let me just be very ambitious and let me say lambda stands for all possible models of the universe, or at least all possible models in a particular subdomain of science. And so lambda may enumerate a discrete number of models, but it could also contain continuous parameters that are part of these models. So I could say there is Ptolemy, if I go back to our planetary orbits, with some parameters, the parameters you need to define your circles and epicycles. There is Kepler with the parameters needed to describe the elliptical orbits, or there is Newton, but maybe we even have a modified Newton. We could say the force is 1 divided by r to the alpha, and this alpha is still a parameter which we claim we do not quite know. So this is the kind of models we are now talking about. And then we could say there is a P of lambda which is a prior over models. Now you see here's where it gets crazy, because it's not easy to come up with such a prior, but people of course are trying, and there are smart ideas. And one idea we will discuss later is that if you think you can write down your model in terms of, say, an equation, like the right-hand side of a differential equation of motion, then you could say, let me count the number of mathematical terms in this equation. And if there are less terms, then I claim the prior probability for this model is bigger. It's still a choice, but it's a reasonable choice that leads to some interesting insights. So what the observations, the experiments then are doing is they are pinpointing the model, by which I mean they shrink this distribution over models. So to speak, in a very simplistic manner, if previously my distribution over models was very broad and I didn't know very much, then afterwards I have a narrower distribution and I know more once I've done my experiments. It's maybe even smarter to say not that you are necessarily interested in shrinking this space of all possible lambda. It may even be a little bit difficult to count lambda. You can look at the entropy, that's true, but otherwise it's a little bit difficult in a high-dimensional space to say whether you are really shrinking. But what we are really interested in is whether our models that we're making are becoming very predictive. So we could introduce other variables of interest besides the observations y that we are using in our experiments. And we could say that if the probability distribution over these other observables that are of some practical interest, maybe interesting for the engineer, if that probability distribution shrinks and becomes narrow, then this is a success. And this can happen even if multiple models, multiple different values of lambda are still consistent. And they could even be very different if the P of Z given lambda for the practically important quantity Z is basically the same for all these lambda. And we don't care whether the distribution over lambda is still very broad or not. So if we are happy if for all observable Z of practical interest, the models start to agree after we have updated the model distribution given our experimental observations. Now you understand this is all very vague, and it's a field of current research of how to actually implement this program. But you see that in principle, conceptually, Bayes is what you should use to do science in the world. You observe something, you update your knowledge, you shrink the space of possible models that are consistent with your observations. And so if you are a very rational person and very smart, then you learn how to, in science and everywhere else, how to always ask those questions first that are likely to reduce the entropy the most in order to give you a lot of information, even though you have asked only a single simple question. Okay, I think that's enough for today, but maybe there are already questions. I promise that next time we will discuss this thorny issue of the prior, because you have seen the prior is always a question mark. We can say a little bit about this. And then we will discuss cases where the models are no longer just a single variable like Qubit state or a photon number, but they are already a little bit more ambitious. So the models will be functions. So lambda stands for a function. Okay. I don't see any questions at the moment. Then I would say, see you on Wednesday. Goodbye.